start record. That's good. No, I asked him to do that. I asked him to. Otherwise, I get a lot of really sad emails on like Monday morning from people who are trying to get their homework done. And I go, "Where's the lecture?" I said, "I'm sorry, there is no lecture. You're gonna survive." Okay. All right. Are there any questions, comments, concerns before we get started today? Any questions about the project? I know we've talked about it a bunch. Yeah, again, it does not have to be, like, I don't expect everyone to be freaking Daft Punk and putting out some crazy stuff. Like, as long as you're just making some notes happen, it's all good. For Hunter, I knew it, Hunter. I knew it. If I posted the homework before class started, someone would ask me a question about how to do the homework. So I posted the homework. It's just you have to do a couple of these examples. So we're going to do some examples of taking the sequence, doing the Z-transform, getting the rock plot, and all that fun stuff today. And then your homework is just do like a handful of them that are just like this. So Hunter asks, for the homework assignment, how does the Dirac affect the summation? The textbook has a table of Z-transforms. You will find what happens to, like, what the closed form solution of that Dirac function is in the table in the textbook. So when in doubt, go to the table, copy it down. So I don't know off the top of my head is what I'm saying, Hunter, because I just look at the table. So yes, so I have to read the textbook? Yes, you have to read the textbook, Hunter. or just Google Z-transform table. Yeah, no, that one's due next Monday. You just turned it in? All right, well, go to sleep, Curtis, because then you're good. You don't need to hear any of this. Have a good weekend, man. All right. Yeah, I knew it was going to cause trouble if I posted it early. I was just too lazy to like check the box that like scheduled it for in advance. All right. So today, like I said, we're just going to do some examples of the Z-transform and finding the region of convergence and all that fun stuff. Hopefully, it'll be pretty quick. Well, actually, I take that back. It's not going to be very quick because it takes a long time. But it won't be too boring for everybody. You all can go back to making sweet music in Python. Okay. So here's all we want to do. Find the Z-transform of the signal x of n is equal to 1/2 of n times u of n plus minus negative 1/3 to the n times u of n. So it makes this one special. Oh, you guys are really want to see the screen, huh? Edward, why didn't you tell me to post the stream? That's on Edward. That's not on me. Hold on, I want to change. I don't want to do that. I want to do this one. Stop. Share. Screens. Screen 2. Go live. All right, much better. The screen. All right.
Frantically trying to get us to talk to work.
Why can't I unmute? All right. Now everyone can see the screen. So yeah, so find the Z-transform of the signal x of n is equal to 1/2 to the n times u of n plus negative 1/3 of the n times u of n. So all we're going to do is just plop that bad boy into our basic Z-transform function. So x of z is equal to the bilateral sequence negative infinity to positive infinity of all of this business. So 1/2 n, u to the n plus negative 1/3 n, u to the n times z to the negative n. Done, right? We can all go home now. Okay, so we want to take advantage of linearity. The best thing to do is just kind of break it up a little bit. you want to sort of get it into the smallest chunks that you can. So we'll take advantage of linearity to go ahead and rewrite it like so, bilateral sequence, 1/2 n times e to the n times e to the negative n plus another bilateral sequence, negative 1/3 n times e to the n times e to the negative n. Now, once we've done that, the next step is we want to essentially take advantage of u of n to make it into a sequence that has a closed form solution. So x of z is going to convert everything into a unilateral or right-sided sequence. So that's going to be n equals 0 to positive infinity of 1/2 n times z to the negative n plus right-handed sequence negative 1/3 to the n times z to the negative n. Next up, we got to get everything into our geometric sequence form, because that's kind of where we want to always end up. So with that nice, neat geometric sequence. Equals 0 to positive infinity. So remember, z to the negative n, make a note over here, z to the negative n is equal to z to the negative 1 to the n. So that means we'll write it as 1/2 times z to the negative 1 to the n plus the other side minus 1/3 z to the negative 1 to the n. All right, that was some stuff. Are there any questions about how we got to that point? It's basically the same thing we saw last time. We're just doing it twice at the same time. Okay. Next up, we need to get our closed form solution, and here's where we just go to the table. We look and see what we got for our geometric sequence. So that means that we're going to get x of z is equal to 1 over 1 minus 1/2 z to the negative 1 plus 1 over 1 minus 1/3 z to the negative 1. All right, now from this, we've got to do some weirdness, because we need to get it all in one form. So we have to add everything up to get it under a common denominator, because remember, we have to get it to this form, right? X of z is equal to p of z over q of z, right? So that's the form that we've got to get to. So now we're just adding two fractions. So we'll have x of z is equal to 1 minus negative 1/3 z to the negative 1 plus 1 minus 1/2 z to the negative 1 over 1 minus 1/2 z to the negative 1 times 1 minus negative 1/3 z to the negative 1. Then, let's see, we just simplify a little bit. We have 1 plus 1 is 2. Minus negative 1/3 is going to give us plus 1/3 z to the negative 1 minus 1/2 z to the negative 1 over 1 minus 1/2 z to the negative 1 and 1 plus 1/3 z to the negative 1. Most of this entire exercise is just doing algebra. Okie doke. So let's see. One last thing I want to do is 2 plus 1/3 minus 1/2 is minus 1/6. So minus 1/6 z to the negative 1 over that same denominator. 1/2 z to the negative 1. 1 plus 1/3 z to the negative 1. Okay. And I know for some of you guys it's probably boring that I'm like writing out every single step. I'm going to do it anyway, just because, I don't know, I always hated those guys that like set it all up and then were like, well, in the end it's obviously this, and you kind of wanted to see what was going on. So that's why I take the extra time to write out every step. And I apologize if you find that to be somewhat dry. Okay. The next thing we want to do is we want to do two things. We want to get rid of this business, right? Because we want everything to be kind of nice and neat in terms of like 1 and z and stuff like that, so we can get our poles and zeros. So I'm going to do this. I'm going to factor out the 2 and get 1 minus, that's going to be 1/12 z to the negative 1 over all of that. 1 minus 1/2 z to the negative 1. 1 plus 1/3 z to the negative 1. And then the last step is to get rid of all of the z to the negative 1s by factoring them all out. And what that basically will do for you every time is just this, the z flip side, since you're going to get 2z times z minus 1/12 over z minus 1/2 and z plus 1/3. And there we have it. There's our nice, neatly factored, closed form solution to our z transform. Okay. Any questions about how we got that? Like I said, not anything like too super complicated. Mostly just a lot of sort of tedious algebra.
Is that a continuous function?
Is what a continuous function?
No, x of z.
Yeah.
Yeah.
Uh-huh.
So we went from discrete to continuous when we plugged in the summation formula for the geometric series.
Yes.
Okay.
Why do you ask?
No, I just noticed a notation difference.
Oh, yeah. Okay. Cool. Okay. So next thing we want to do is we want to plot the region of convergence, because it's really the part that we care about. Plot the region of convergence. And we're going to say with. Now we're going to take into account the poles and zeros. One important note. To get the rock, use the series form of our z transform, the one that we started with, and then to get the poles and zeros, use the closed form. Of x and z. And what I mean by that is, so to get the rock, we're going to start with that closed form. I'll go ahead and write it down again so we don't have to scroll up to the top. But it was this, x of z n equals 0 to infinity, 1/2 z to the negative 1 to the n plus this series from 0 to infinity of minus 1/3. z to the negative 1 half, or z to the negative 1 to the n. And since we have two pieces here, we're going to compute two different regions of convergence. And they kind of, our series will only converge where they overlap. So, if we look at that series first, well, we know that since it's a geometric series, the absolute value, 1 half z to the negative 1, must be less than 1, which means that 1 half times 1 over z, all of that absolute value must be less than 1, which means that the absolute value of 1 half must be less than the absolute value of z. So, due to the first part, right, our region of convergence will be there, right? Z is less than 1 half. The absolute value of z is equal to the absolute value of less 1 half. Now, if we come over to this side, well, we're going to have that minus 1/3 z to the negative 1 also must be less than or equal to 1. Since the absolute value is right, it's just 1/3 times 1 over z must be less than 1, so we have that 1/3. Its absolute magnitude must be less than the magnitude of z. So we have two pieces here, right? So where is our region of convergence?
So the region tells us that both converge, right?
What's that?
That both of those have to converge.
Right, so that says that the first one converges when z is greater than 1 half, and the second one converges when z is greater than 1/3, right? So what that means is, well, first off, what's bigger, 1 half or 1/3?
1 half.
Right, if we just number line this guy. Right, and we have 0, and we have 1/3. No. Come back. And we have 1 half. Right? So the one we've marked here in orange converges for z greater than 1/3, right? And the one we marked in green converges for greater than 1 half. So what does that mean about that region? Is it going to converge or diverge? You just flip a coin, right? It's going to diverge. Why would it diverge?
Because the other half doesn't converge there.
Because the other half doesn't converge, right? It makes sense if you think about it, right? If I have, right, two guys and both of them are finite, right, then my combination is going to be finite, right? But if I have one guy that's shooting to infinity, well, it doesn't really matter what the other guy is, right? The whole thing's going to infinity. So yeah, so it's only going to converge where everybody converges. Not it's an and operation, not an or operation. So that means that our region of convergence exists for z greater than 1 half. So we can apply it. We're going to have our real component, our imaginary component. Let's draw our circle right there, and we know that it's going to converge outside of that region. All right, now for the poles and zeros. Eventually, the poles and zeros are going to tell us an awful lot about what our system does, but for now, we don't really care. So to do that, we go back and get our closed form solution, which is what, 2z times z. So we go to the closed form. X sub z is equal to z times z to the minus 1/12 over z minus 1/2 times z plus 1/3. So what that means is we have poles are going to be everything that's in the denominator. Poles where it goes to infinity, right? So poles at z equals 1/2 and z equals negative 1/3. So we come back up to our drawing. We're going to say that we've got a pole, which we'll denote as an x for now, at 1/2, and a pole at negative 1/3. Notice that I am saying that the pole is negative, not taking its absolute value. And zeros are everywhere that our function is 0. Zeros at z equals 0 for the 2z, and z equals 1/12. So I'm going to have a 0, and I'll just like draw a dot for 0, and that's not really the scale, but my next 0 will be down here at 1/12. So there we go. They were taking a sequence, calculator figured out its z transform and plotted its region of convergence and its poles and zeros, man. It's not nothing. Any questions about that? All right. So that was a fun part. Now let's go ahead and eat some vegetables. And we need to list out the properties of the rock. So a few of these we already talked about. One, the rock only exists in the form, let me say this, 0 is less than or equal to r is less than or equal to z. This would be the whole, like we talked about last time. Or it can be 0 is less than or equal to, we'll call RA, is less than or equal to Z is less than or equal to RB, which is less than or equal to infinity. This is the ring. Or Z is less than or equal to R is less than or equal to infinity. This would be the disk. So those are the forms that it can take. Property number 2, the Fourier transform. For a sequence x of n converges if and only if the rock contains the unit circle. Which is r equals 1. So this basically says that for a sequence, it is possible to take a Fourier transform of a sequence only if our rock includes the ring that is r equals 1. If it doesn't, then all kinds of weird stuff is happening. Three, if x of n is finite duration sequence, which is to say, just an actual like finite sequence, nothing that goes to infinity or negative infinity, then the rock is the entire z-plane. Which makes sense, right? Because if our sequence is finite, which means it only sums to some finite amount of numbers, then its convergence is going to be everywhere, and so it will converge for everything. Its region of convergence will be infinite.
Can R only be a real number?
For the purposes of this conversation, yes. I'm missing one. Oh. 4. And these next few will save you a little bit of time and work. The rock cannot contain any poles. So if you got poles, which makes sense again, because poles are where our closed form solution shoots to infinity, obviously it doesn't converge there, so the rock cannot contain any poles. But this is helpful for doing your regions of convergence. 5, if the sequence is right-sided, i.e. n goes from 0 to infinity, like the ones that we've already seen, then the rock extends from the outermost pole to infinity, right? Which is what we saw in our example. We come back and look at this. We had that both of our sequences here were right-sided sequences. They extended from 0 to infinity. And our region of convergence contained neither of the poles, negative 1/3 or 1/2, but it extended from the outermost pole. So 1/2 was the outermost pole, and that's where our region of convergence started. So by that rule, you don't actually have to go looking for, you don't have to go back to the series form and figure out what your stuff is. You can just look at the poles, and the poles are going to tell you what your region of convergence is.
Can you scroll over to on the right for the orange thing that you wrote? Yeah, I can't really see it at all.
That's good.
So once we have our Z transform, do we ever work in that domain with like let's just use the project, let's say. Like we have a sequence of numbers. Once we have like some sort of transform, do we always need to bring it back to the sample domain, and domain, and then operate with our input like that? Or can we ever work within?
Yes, so the question was, for those of you guys who couldn't hear me, was saying like, is it once you have your Z transform, is there ever a reason to like go back to the sample domain? Which basically is to say, would you ever take the inverse Z transform of a function? That's absolutely yes. That's the whole point of this. Is what we're going to do is we're going to actually, when we go to design our filters, we're going to design them in the Z domain, right? We're going to essentially say, it turns out that we can, by picking the poles and zeros that we want, we can get the effects that we want. This type of filter or this type of audio effect or whatever. And then what we'll do is we'll have to take the inverse transform, and that's going to give us our impulse response function that we're going to convolve with our signal to do the thing that we wanted to do. Yeah, so we'll actually start our work in the Z domain, and then once we're finished, we'll move to the sample domain and then go on from there.
Okay.
All right. Let's keep chugging along. A few more of these. Okay. 6 says that the sequence is left-sided, i.e. n equals negative infinity and comes to 0, which is a thing that can happen, the rock will extend inward from the innermost pole. Seven, a two-sided sequence will have a rock that is bounded by poles but not containing any poles. All right. And finally, the rock must be a connected region. Which is to say, there can only be one rock. There cannot be multiple rocks. Surely there's a place there for a Dwayne Johnson joke, right? All right, any questions about any of those rules? Basically, the reward you get for listing them is you never have to look at that series thing once you have the poles and zeros. You can just look at the poles and zeros and say, ah, yeah, this is what I got. So, minus noting what side the sequence is on. So, yeah, let's do one more example.
Can you scroll a bit back to 7?
A two-sided sequence will have a rock that is bounded by poles but not containing any poles. So example, plot the rock for the sequence. There we go. X of n is equal to minus 1/3 n times u of n minus 1/2 n times u of negative n minus 1. So, first thing we do is we just quickly take our sort of raw z transform and then we'll simplify it. N equals negative infinity to positive infinity of all of, I'm not going to be lazy. Minus 1/3 n e to the n minus 1/2 n u to the minus n minus 1 times z to the minus n. Just like before, we will take advantage of symmetry. Let's bring everyone together. N equals minus infinity plus infinity minus 1/3 n u to the n z to the minus n minus the bilateral sequence negative n or infinity, negative infinity to positive infinity of 1/2 n times u to the minus n minus 1 z to the minus n. Okay, so really quickly, so now we have, hold on, let's do one last thing. Let's see. How do I do this? let's focus on the right-hand side because we've already basically done the left-hand side, right? We can already tell, we did this in the last example, exactly this sequence. And so we got that we had, it turned out to be z, well, first off, it became right-sided, right? It had a closed form solution, z over z minus 1/3, which means that it has a 0 at z equals 0, and a pole at z equals -1/3. Cool? All right, so let's focus on this side because it's a lot more interesting. So we've got, whoa. All of that stuff minus infinity, positive infinity, 1/2 n u to the minus n minus 1, z to the negative n. So what's going to happen here is this, that u to the minus n minus 1 is going to turn our sequence into a left-sided sequence, which is to say we're going to go from n equals negative infinity to -1 of 1/2 n z to the negative n. Okay. So this is a left-sided sequence. This is just a note that we will keep forever. But we still need to get it into a closed form. We need to figure out what we're working with. So the first thing that's going to happen is we're going to flip everything over. I am not a mathematician, and I do not know why this next part works. So I just need you to trust me that it works. When we flip everything over, we're going to get n equals 1 to infinity, 1/2 negative n, thank you, Edward, z to the n. And I didn't take the time to sit down and figure out why it works. But it just does. It just works, man. Go over to the math building and ask them why it works. I'm sure someone can tell you, but I cannot. But yeah, so we want to flip back over to get that right-hand side of business. And so, let's see. All right, we're not quite to our closed form solution because we have n equals 1, right? Our thing still has to kind of live in that n equals 0 to infinity place. We still want to get it to that geometric sequence thing. And the way we can do that is essentially by adding 0 to the expression. So if I were to set n equals 0 over here, what would I get?
1.
What's that?
Yeah, 1.
I would get 1. Well, I would get minus 1, right?
Yeah,
Because of the negative that's hanging out there. So minus 1. So what I need to do, if I want to convert this back to n equals 0, I need to say that it's 1 minus n equals 0 to infinity of 1/2 minus n z to the n. Now I can do the stuff. All right. Now I've got 1 minus 0 to infinity, 1/2 minus 1 times z to the n. It's going to be the same as 2z to the n. Now I've got my geometric series, so it's going to be 1 minus 1 over 1 minus 2z. Again, I have to combine everything under one common denominator, or over one common denominator, I should say. So I'm going to have 1 minus 2z minus 1 over 1 minus 2z. All I did was multiply both sides by the common denominator. 1 minus 1 is that, so I'm going to have negative 2z over 1 minus 2z. And then I'm going to factor out minus 2z from that bottom expression, minus 2z over minus 2z times, that's going to be 1/2, or minus 1/2, z to the negative 1, it should look familiar to us now, plus 1, those factor out. So I'm kind of rushing through the algebra just a little bit, but that leaves us with 1 over 1 minus 1/2 z to the negative 1, which lovingly is z and z to the minus 1/2. Which means that we have a 0 as z equals 0 and a pole at z equals 1/2. Now we're ready to plot the thing. Are there any questions about how that works? Hunter is absolutely right. If you do the thing and you don't mess it up, it just works. As long as you don't mess it up. All right. Any questions about all the algebra that we just did? All right. So now let's recap that left-hand side there it was right-sided with zeros at z equals 0, a pole at z equals 1/3. Over on the right-hand side, we had a left-sided with a pole, but also a 0, 0. And a pole. I should take it back. It was negative 1/3. And a pole at z equals 1/2. So since we have a right-sided and a left-sided sequence, what is that going to mean for us? What's our rock going to look like? A two-sided sequence, which means our rock is going to be a disk, a hole, or a ring. This is it. If you answer this question, it gets to be the weekend. It's a ring, yeah. So yeah, so it's going to be a ring. Right, because it makes sense. Well, let's just draw it. Then we can talk about how cool it is. Why did you do that? I don't want you to be pink. Close enough. All right. No, it's not. Because I made a comment about it being the weekend. All right. Real. Imaginary. So let's go ahead and draw our stuff. So we had what? On the left side of the thing, we had a 0 at 0, and we had a pole at, let's put it out here, at 1/2. And then we had a 0 at 0 again, and a pole at negative. Right there. Negative 1/3. Right? So that means that since the green one, the first one that we looked at was a right-sided sequence, that means that its region of convergence extends outward from its farthest pole, and the left-sided sequence extends inward from its innermost pole. They both only have one pole, so it's pretty easy. And of course, convergence just exists where it exists for both of these guys. So we have one there, and is it there? Yeah. Like that, which means our region of convergence that is that. All right, and there you go. Any questions about that? All right, your homework that I think I'm gonna make due on Wednesday instead of Monday, just because I don't like making you guys do stuff over the weekend, is just this. I think there's 5 of them. They're pretty simple. Some of them are like just the unit step function, and some are just the delta function. So they're pretty easy, just to get you guys some practice working with the sequences, finding the poles and zeros, plotting the rock, and moving on with your life. So, any other questions, comments, concerns? Cool. Don't forget that project is due tonight, right?
Yeah.
At midnight. Like I said, again, it doesn't have to be a serious, beautiful song. It's just got to be something that vaguely resembles music. Vaguely. Like I said, all I wanted it to be was just, you know, a slightly interesting way to like make some signals, stick them together in an interesting way, and produce something fun. So, if there are no other questions, comments, concerns, have a good week and be safe. And I'll see you guys on Monday. Thank you. Enjoy the football game.
You guys are watching UFC this weekend. Have a nice weekend.
You too. Thank you. You said, am I watching UFC this weekend?
Yeah.